So I have all the exams graded for this section. I'll wait till I have all my sections graded to determine if I have a curve, but based off of you guys, the average was like the mean and the median were right around like 75, or I think 75, 76 was the mean, and the median was a little bit higher, like a 78. So the average is kind of right where I want it to be. So I don't expect kind of a curve or anything like that. But like I said, if I grade the other sections and I see something different, I might have something to kind of add about that on Monday. Okay. So if you have any questions over the grading on that, I left all the comments on Canvas on your exam about why certain points were taken off on the short answer. There was an issue with one question that it was originally set to the incorrect answer, or sorry, it was accepting the incorrect answer. So I had that regraded, so everything should be working correctly now. I believe it was question number 7. So if you're seeing that and you're having questions on that and it didn't regrade it correctly, please let me know. But as far as the ones that I've looked at, it looks like it's working correct. Other than that, I have that. I'm going to show you on Canvas. We've got, oh, clicked on the wrong tab. That doesn't help. All right. So I posted an announcement. I tried to mention I've had a couple people reach out. This was just a practice problem. Like, these are just practice problems. This isn't. It says it's worth 160 points. I'm leaving it in this category that is 0% of your grade. It was just there for practice, so you didn't have to do this. However, after class on Wednesday, I posted this Learn Smart. This is due before we start. This should be set to AM. I'll go in and change that. So I want you to have this read before we start class on Monday, okay? So before we start class on Monday, I want this Learn Smart to be done. And I also posted this morning kind of the next Connect assignment. So the due date on that's kind of off a ways, kind of 2 Fridays from now. So as we work through these problems in class, I would kind of start trying to chip away at that Connect assignment. I'll tell you right now, I'll give the 5th Connect assignment as well. We'll kind of overlap with this one. However, if you kind of work, next week, look at the questions, they're in order. So start chipping away at those questions as we progress the material. That's going to make that a lot easier. A few, not quite as many questions as the first couple. And so that also will make it a little bit easier there. So I haven't kind of posted the exam like where I take these grades and put them out of 100. You'll likely see that kind of get up on Canvas over the weekend, as well as me identifying what your highest and lowest exam score are. So on Monday, I'll show you on Canvas exactly what that looks like. But over the weekend, I will be doing that. So if you see that, that's why. Okay, kind of because everyone's, not everybody's best exam was the first exam or the second exam. So I'll have to kind of create some new, what looks like assignments to just kind of categorize those. That should kind of cover all the housekeeping stuff. If there are any questions for me before we kind of jump into material here. Okay. All right, so we'll be working with this 2-population HT blank file that's up on Canvas under the in-class data folder. So if we go to files, in-class data, this guy right here, and we'll work off the blank one. Okay. But before we do that, let's pick up where we left off last class. I can find it. 1, 2, there we go. So we left off in this example, and I kind of showed you how we identify the null and alternative hypothesis when it comes to these differences. So we'll kind of pick up using that null and alternative hypothesis for this question, which was, have tropical storms increased kind of in more recent years, right? A newer time period versus the older time period. So this is our group 1. Here's our group 2. Group 1's the newer years. Anytime we look at years or like changes over time, you always want to kind of put the newest years first, right? Because that way, when you take group 1 minus group 2, new years minus the old years, well, if it's positive, that means they've increased. If it's negative, that means they've decreased. If we look here, we have a right-tailed test, right? We have a greater than sign in the alternative hypothesis. So for a right-tailed test, if we're thinking about critical values, those critical values should be what sign? Well, if they're on the right side of that distribution, switch over the dot key here because I'll start using this. So we're thinking about the critical values this is an example where we have two means and we know population variances. Right? So because we know the population variances, I can use that standard normal or that Z table, Z distribution. So what I want to find is the critical value, and I believe that I said the alpha was 0.05. That gives me alpha to the right, okay? So the critical value is coming from this standard normal or Z table, so it's going to be a Z value. And I know the area that I want in that right tail is 0.05. So we already said, because it's on the right side of this distribution, it should be positive, right? Because this distribution is centered around 0, mean of 0. Now I can do this two ways. I can simply look up alpha. If I do it that way, well, remember the table's always looking at the area to the left, so it's going to give me the right value. It's just going to give me the negative value. I could also look up, well, if I know I want the positive value, and I have 0.05 in the upper right tail, there would be 0.95 in that lower left tail. Right? So I can do it either way, and I'll show you both here right now. So we'll wait in class for this to pop up here. There we go. Oh, all right, there we go. So we know it's going to be one of these values, right? We know it's a positive value. So let's go to our standard normal table, Z tables. Let's make it so you can see what I'm doing. All right. So I know the area I wanted in that tail was 0.05, but I wanted it in the upper right tail. So I said I could look up 0.05. So I'm hunting here. Looks like it's in between these two, right? So 1.6, 4, and 5, in between negative 1.6 and negative 1.65. I'll take the higher of the two, or negative 1.65. But remember, it's a right-tailed test, so I just need that value, but positive. So positive 1.65. I could have also remembered, oh yeah, I could look up the area to the left of that critical value I want, which was 0.95. Not use this idea that the distribution is symmetric. If I hunt down 0.95, look at it's in between these two values. So 1.64 and 1.65, higher of the two, 1.65. That's exactly what I got doing it the other way as well. So either way is fine. If it's harder for you to think about this distribution being symmetric, then you don't have to do it that way. You can kind of draw out that picture. Remember, oh yeah, I need to look up the area to the left on the table. The area to the left would then be 0.95. Okay. Any questions on that? So we just found this is what? Positive 1.65. Okay. So from there, oh, I'm going to close this because this is not, got two of them open for some reason. There we go. So from there, I now need my test statistic. Okay. I mean, this is really just a matter of, we have our new test statistic equation. So if we go back, last class, we kind of showed you why this is what it is compared to what we're doing with one population. It's really just a matter of plugging in all my values. I have the sample means, I have the population variances, I have my sample sizes. That assumed true difference is going to be the value that's in our null and alternative hypothesis, which I said in almost all the examples we'll look at, and all the examples I would expect you to do on the exam or homeworks, that value is going to be 0. Okay? So that makes it a little bit easier. So before I'll show you the calculation, but here what I'm thinking about is I'm looking at this statistic, which is the difference in sample means. Okay? I know that's going to be normally distributed around whatever the true difference is. Well, I don't know the true difference, but I have this assumed true difference of 0. Remember, we can almost think about this as, this is like the sample difference that I found. Okay? So if I go back to that example, I forget what the values are. We've got what? Group 1 was 15.5. Group 2 had a sample mean. I say group 2. The new years minus the old years. So 15.5 minus 9.7. Right. So 15.5 minus 9.7 would be what? 5.8. So I found this sample difference of 5.8. Well, if I want to turn this into a z-score, it's going to be a certain number of standard deviations above that assumed true difference, right? Because it's on the right side of that difference. So I know my test statistic should be positive. Okay? I can't really say much more than that at this point, but I know that it's going to be positive, so I can rule D out here right away. Okay? Now, from there, it's just a matter of, we've got that equation, it's just plugging in our values here. Right? Once we've identified this is the formula we use, I really can't help you a whole lot more at this point, right? We're plugging those values in, and then it's just a matter of getting it entered into our calculator correctly. Okay? So I end up with this test statistic of, what, 4.9? Now, I don't know how familiar we are yet, right? Hopefully we're getting pretty familiar with thinking about what these test statistics and these different z-values mean. Okay? So z-values, if we just look at the table, I mean, the table only provides us z-values from what? 3.9 to negative 3.9. So if I think about this here, the area to the left of 3.9 would be approximately 1, which means the area to the right would be approximately 0. So if the area to the right of 3.9 is approximately 0, and I have a test statistic of 4.9, what would the area to the right of 4.9 be? Even closer to 0, right? So when I'm thinking about what I'm looking at here, my critical value is 1.65. And I can think about, sometimes I use arrows to identify that rejection region. Well, I just found a test statistic of like way out here, 4.9. Remember, I didn't even have my curve drawn out this far. Remember, the area for a right-tailed test, the p-value would be the area to the right of my test statistic. And I know that that area to the right is approximately 0. So I've got this p-value. It's approximately 0. Okay. I mean, anytime I see a test statistic over 4, I should think like, the probability of seeing that or anything more extreme is pretty much 0 there. Right? I can't actually, without using Excel, I can't get any more exact. So if we think about our rejection decision, it is the p-value less than alpha. Well, our typical alpha values, I can move my papers here, 0.1, 0.05, and 0.01. Well, 0 is going to be less than all of those, so I can reject at every single level here. I found sample evidence that was quite a bit of a distance away from that assumed true difference. I see how many standard deviations was it in fact away? Well, 4.9 standard deviations away. Okay? Which is, like I said, we'll start getting used to. That's quite a bit. Right? Any questions on anything there? You can also think about, before we turn this into a test statistic, we have this right-tailed test. Right? Any questions on that? Nothing in the chat. Okay. So, I believe before we kind of keep going on with the slides here, and I'll work through a few of these by hand as well to kind of show you what we're doing. But we're going to go to Excel. We're going to go over to this Midwest data sheet first. Right? I'm going to zoom in on this just so we can see it. So I had, a bunch of different universities in the Midwest, a sample of them. I've got their total undergraduates, and I've got some other information as well. But we're going to focus on this total undergraduate variable. So all I did there was I found my sample mean, right, using the average function. I assumed that I was given this population variance of what, 75 million, right? So here, we're going to start out with these examples where we know the population variance. It's not the most realistic or applicable scenario. We usually have to find the sample variance, but we need to start out here, and then if we only have a sample variance, we'll say discuss those changes. So I've been given this population variance. I use that count function to find my sample size. So I've got sample mean, sample size, and a population variance for the Midwest school sample. I'll then go over here to this South sheet. Right? And what I'm going to do, or what I actually have already done, is up here, I've got now my Southern schools on this data sheet. I'm going to find the mean enrollment. I was given the population variance, and I calculate the sample size for those South schools as well. We've done a lot of this stuff already. There shouldn't be anything new. One thing that is new that I did here, and I shouldn't have to do this on any of the on the next Excel assignment, but you might see something kind of weird here. If we ever have data on a different worksheet, so notice I'm in the South worksheet here. If I just put an equal sign, and then I go to a different sheet, it starts to put the reference that, okay, I want you to take a value from this other worksheet. What value do I want? I want that sample mean, just so I can have all my data in one place. I did the same thing for the population variance and the sample size. I'm just referencing those values that were on the other sheet. So now I've got everything here. I've got my two samples, the South and the Midwest. I've got their sample sizes, sample means, and population variance. Well, that's all I need to start doing things like confidence intervals and hypothesis testing. So we'll start out with confidence intervals. If we go back to last class, here we've got kind of the lower bound equation and the upper bound equation. We've got all these values in Excel except the z value, right? So we're going to find that z value that gives us alpha total outside the interval, which means alpha over 2 on each side. So this is going to be just like, and I know we didn't spend as much time on how we do hypothesis testing in Excel with one population. We'll spend a lot more time for these two population examples. But the formula that we can use is, well, we know the area in the tail, and we want Excel to tell us that z value that gives us alpha over 2 in the tail. So that was the norm.s.inv. I'm using a standard normal distribution, and I'm working in reverse. I know the area in the tail, and I want the z-score. So alpha divided by 2. This should give me that z-score. Now, the issue is, because it's always looking at the left tail, it gives me the negative value. Well, the negative value and the positive value are kind of already built into my upper and lower bound equation. So here we just want the absolute value. Probably the easiest way to do that is use that absolute value function. I could have also done 1 minus alpha over 2. Right? We looked at that when we did confidence intervals for one population. This is really no different. There's just, finding the z-score is the exact same for 1 or 2 population confidence interval examples. So I then copy this down. Now have my z value to build each one of my confidence intervals, the 90, 95, and 99% levels. So from here, it's just a matter of using Excel to be a calculator. Right? So I had that confidence interval equation. What was I going to base that confidence interval around? Well, it was going to be, here I think I said the Midwest, the difference between the Midwest and South. So I've defined group 1 as the Midwest, subtract the sample mean I found from group 2, which was the South. This will be the sample difference I'm building my confidence interval around. For the lower bound, I'll then subtract that z value, right? And I could enter this all in one line, but I'm going to show you here kind of what I think is probably an easier way to do this. So I then would multiply this by the standard deviation of the difference in my sample mean. So I'm going to calculate that up here, and I'll show you why that's a little bit easier. So for right now, we're going to take a little step out of this cell. So if I want to calculate the standard deviation for the difference in my sample means, what that was really just this guy right here, right? I was just plugging that in and doing it all at one time. We worked through examples last class where I said probably easier to do the intermediates, like calculate that intermediate value. So that equation is just to take the square root of each group's population variance divided by that group's sample size. Can't click on this here because I have some weird setting. So it's an M6 plus the population variance of the other group divided by its sample size, right? And now I kind of have that intermediate value calculated. So notice I was referencing that up here, and it made this just a little bit easier. If you look at, here I don't think I have it open, but I can get it real quick. If you look at the completed file, oh, come on, there we go. So if we look at, I can click on this, my toolbar won't go away. There we go. So I had this all built in already. I did it all in one line here. Kind of notice there's just a lot more to look at. There's a lot more going on. I end up having to freeze a lot more cells. So you can do it this way, and I'll post what we do here in class because I think honestly calculating the intermediate value here just makes it a lot easier. So when I copy this down to build the lower bounds for each of my next confidence levels. The only thing I want to change is this z-value. So I'm going to make sure that these sample means stay the same because I'm still building my confidence interval around the same sample mean. So I'm going to hit F4 or Command T on a Mac. I also need this standard deviation of my sample means to stay the same. So I'm going to freeze that cell as well. Now when I copy this down, keeps those the same, just uses a new z-value. Now to get my upper bound, it's going to be this exact same equation. So I'm going to highlight that. I'm going to copy it, hit enter to get out of the cell. I'm going to go over here and paste it. So when I copy paste this way instead of dragging it over, it doesn't update any of the cell references. The only thing I need to change for the upper bound is I'm adding that margin of error. Right? Once I've done that, copy down, and I've got my 3 constants. So this is very similar to what we did with one population. It's just that this standard deviation equation is a little bit more complicated, so it kind of makes it easier to do that intermediate calculation. And instead of just one sample mean, we're basing it around the difference that we found in these 2 sample means. Okay. Any questions on any of that, or you want to see another cell again, or wait for people on Zoom? Okay. So I'm going to change this here. I think we're going to, I don't have these values in here. So what we're going to do here is a right-tailed test. Why does this look goofy? Because I don't have it aligned right. So I'm going to start out with these values being what I told you we'll always use, which is the assumed true difference of 0. Okay? I've got a greater than sign here, so I'm going to be doing a right-tailed test. So it's going to line up kind of similar to what we did in that last example. But one thing I can do in Excel is just use Excel to be my calculator and calculate this test statistic. Right? So we just dealt with that formula, which was right here. So I'm basically just going to, I have all the information I need in Excel, so I'm just going to click on the values in Excel and have it be my calculator here. Okay? So the thing that's in the numerator is I'm going to take the difference between the Midwest, right, minus the South's sample mean. So that's kind of my sample difference. Now here it might seem trivial, but I'm going to do something later where it helps to have this assumed true difference in a cell. So I'm going to then subtract that assumed true difference, which is 0 here, so it doesn't really change much. I'm going to make sure there's parentheses around this so that this is my numerator. Then in my denominator, I could actually type this all in again, right? The square root of each group's sample, it's not sample, sorry. Each group's population variance divided by its sample size, but added together. But remember, I already had that up here, right? That's what I was using for my confidence intervals as well. So when I calculate that intermediate value, it makes it a lot easier if I'm doing both confidence intervals and hypothesis testing or multiple hypothesis tests. So I'm just going to click on that. It makes it a lot easier. Okay. Now, similar, so I got 2.61. So if I go to the completed file, I didn't do that. I typed it all in. You can just kind of see there's just a lot more going on. I have to type in that same thing over and over again. I might as well just have it up in a cell somewhere that I can reference. Okay. All right. So we've got our test statistic. Okay. If I want the p-value, what I'm thinking about doing there is, well, I've got a right-tailed test. Okay. So kind of like that last example. I'm using the standard normal because I know the population variance is 2.61. My p-value is the area to the right. Okay. So I've got the z-score, and I want to find the area in the tail. That's not the inverse. That would be norm.s.dist, right? I'm telling it the z-value right here, my z-statistic, my test statistic. And then I'll always use comma 1. Comma 1 gives me the total area to the left. Now, if you put comma 0 in there, remember, it's not giving you the area to the right. It's doing something else. It's kind of goofy, and we actually don't use it for anything in this class, so that's why I say always put a 1 in there. Now, this works the same way as the table. Norm.s.dist is going to tell me the area to the left. I want the area to the right, so I would then have to subtract it from 1. Okay? Well, I can do that all in the same cell. I can actually just put here 1 minus. Okay? So So this will give me my p-value, so 0.004. Now, we can see right away with that p-value that what levels are we going to reject at? Well, we only reject if the p-value is less than alpha. My p-value is going to be less than all of these. So I can reject at every level. We already know that. Okay? I'm going to show you how you kind of construct some stuff in Excel to make it a little bit easier to identify that. So we've got the p-value approach. Before I do critical values, I'm going to show you how you can make, well, I guess I'll call this rejection decision. And that was using an if statement, right? I'm not going to expect you to do that on the homework. You can simply look at the p-value, compare it to alpha. But this is just, I don't know, it's kind of an easy way to do it, I think, when it starts to get us kind of used to some of this different stuff in Excel. So if that p-value is less than alpha, right? If that's true, comma, put in the word, there we go, reject. Comma, if it's false, put in the word, words, fail to reject. Okay? I'm then going to copy that down because I want to be able to do the hypothesis test at each of these 3 different levels really quickly. So I copy this down. Wait, why am I failing to reject? Oh, I forgot to freeze something, right? Because I want the alpha to update here, but I don't want that p-value to change, right? So I'm using the same p-value. So I go back up here, I freeze the cell reference for that p-value. Now when I copy this down, I'm rejecting at all levels, which is what I can clearly see visually is what should be going on, right? My p-value is way less than any of these alphas. Okay. Any questions on any of that? I want to see any of those cells again. Shouldn't be too bad. Okay, so how do I find my critical values? Once again, this is actually exactly what we did for one population. I know the area I want in the tail, right? The area in that right tail, right, is 0.1, 0.05, 0.01. So I'm working in reverse, norm.s, that I and v, standard normal distribution, and I know the area in the tail is alpha. Now here, I can't take the absolute value. Well, sorry, I could take the absolute value, but what I could have also done if we went back to our previous example is think about the area to the left is always just going to be 1 minus alpha, right? When it was 0.05, the area to the left was 0.95. That's just 1 minus 0.05 or 1 minus alpha. So here I'm going to put 1 minus alpha so that I can guarantee it's going to give me my right-tailed critical values. Sure enough, I copy this down for these different alphas. We get that even more precise. Here it's not 1.65 because remember we were in between 1.64 and 1.65. This is going to get us a really, really exact critical value. And after grading the second exam, I can tell some of you used Excel even if you gave me your answers in Word because some of you were telling me critical values of like 6.4448 and I'm like, well, you didn't get that from the table, right? You definitely got that from Excel, okay? Any questions on that one? And just for the sake of time today, I won't work through this, but as a reminder, because we've already done stuff similar to this, so on the completed file, I did it by taking 1 minus alpha, but just to prove it's the same thing, if I just use alpha, and remember it's a right-tailed test, and take the absolute value, that gives me the same values there. Okay. So this is where I'm going to show you something I'm not going to expect you to do, okay? But it is something that you could do after this class. Once you get to some upper level courses, you're definitely going to, especially, I know that the analytics and even in marketing, like you're going to do some stuff called like t-tests. We'll eventually see why we call them like a t-test. We're not quite there yet. It's usually referring to when we only have sample variances, but you'll see something like this where maybe I don't want to use 0, right? So here, when I said that I wanted to use this right-tailed test, the difference is greater than 0, what I'm really saying is I assumed that the difference between Midwest and Southern school enrollments or university enrollments, I assumed it was less than or equal to 0. Right? Well, I can reject that, right? So I can, I found evidence that Midwest enrollment is in fact higher, right? That difference is positive. But now that I know it's positive, what I could say is, well, can I reject if I assume that that difference is less than or equal to, let's say, 1,000? So this is my null alternative hypothesis. This is where it gets a little bit tricky, and this is why I only use assumed true differences of 0 for the sake of this class. What this is saying is, I want to test for whether or not the difference between Midwest and Southern enrollments is greater than 1,000. Or, said differently, do Midwest schools have 1,000 more students, or sorry, 1,000 more students than Southern universities, or even more students, right? So I then assume the opposite is true, and I can see if I can reject that. And I can at the 90 and 95% level here. But I can't quite reject that at the 99% level, right? My p-value gets just a little bit too high here. But you can use other values than 0, and that's why I have it constructed like this. For the sake of what you're going to do, you know, on your on the homeworks, you really don't need this assumed true difference because it's always going to be 0 for you. So it kind of makes it a little bit easier. Makes the equation a little bit easier. But I did want to show you how you would construct this if you wanted to use a value other than 0. Okay. All right, so I think that is good for Excel for today. I kind of outlined last class how we're going to move through this. So this is our first look in Excel. We'll talk about now comparing two population proportions, right? And then I know we won't have time today, but on Monday, we'll then look at how do I do the difference in proportions in Excel, okay? So that's kind of the rest of the stuff on this sheet. That's why we haven't kind of filled in everything yet, right? That's coming next week. So actually, I'm going to save this while I'm thinking about it. All the work that we just did. And I'll get that posted up on Canvas once we've worked through the entirety of the examples. Okay, so we left off, we've done some hypothesis testing, and we knew the population variances. Well, I can also do hypothesis testing and confidence intervals and compare two different population proportions, okay? So it's gonna work very similarly. There's gonna be a couple other wrinkles compared to looking at two sample means, but what we know is going to be true is that if I take a sample of size n, right, and I have a sample proportion, right, p hat 1, so we're just notating this, that the distribution of those sample proportions, where are we at? Did I have it here? Oh, I didn't have it. Okay. Well, I'll draw this out. So I'll kind of say something, then we'll go to the dot cam here. So I know that for my first population, the variance of those sample proportions should be equal to this. Now, that's what we were using for confidence intervals when we only had one population. If I then look at a second population, I know that sample proportion will have a variance that is equal to the same thing, but now the variance of my sample proportions will now be based off of group 2's sample proportion. Now, what I know is true, what I, hopefully we recall from kind of the last stuff we did before the exam, and I'll come back to this slide in a second if you're writing things down. I might actually even write it down here. So what's going to end up being true is that if I look at the distribution of sample proportions, right, let's say maybe here's group 1, it should be centered around whatever that true population proportion is, and the standard deviation, or actually here, I'll make this easier. The variance of my sample proportions was simply, it should be the population proportion times 1 minus the population proportion over n. The problem is I can't observe the true population proportion. All I have is a sample proportion. So that's why we said our best estimate will be if I use my sample proportion to calculate this. I then might have a second group over here. So for my second group, the distribution of their sample proportion will be based around whatever that group's population proportion is. And for that second group, the variance of their sample proportions will be the same exact thing as the first group. It's just that we're using the sample proportion and sample size for that second group. So a similar thing when we're looking at sample means, what's going to be the most common, if we think about now the distribution for the difference in those sample proportions, what's going to be the most common difference I see? Well, the most likely values I see are right here. So the most likely difference that I will find is the difference, the true difference between the population proportions. And then, these values are kind of the next most likely, so these differences are a little less likely. And if I get way out here, seeing this difference is very, very unlikely. So eventually I get to a point where I'm really, really close to the x-axis, or I've got a normally distributed variable for the difference in my sample proportions that's centered around whatever the true difference is. Okay? Everybody with me up to this point? We kind of just, like I said, it's a similar thing that we did for the sample means. Now for the sample means, we said the variance for the difference in sample means was we just added up the variance for each sample mean. It's going to be the same thing here. The variance for the difference in our sample proportions will just be add up, right? We've got the variance for each group right here, so we just add those together. Probably going to run out of room here, so hopefully if you can't quite make out something I'm writing here, please feel free to ask. Okay. So I've got my variance. If I wanted the standard deviation, what's the only other thing I would have to do here? Just take the square root, right? But it's as simple as the variance of the difference in my sample proportions is just add up the variance of each sample proportion, okay? Any questions on that? Still writing, kind of jotting some of this down. Okay, so I want to make sure you guys had enough time to write that down. So if I wanted the standard deviation, it's that same thing, but we take the square root. And notice here, I've got the population proportions written in, but I said we don't have that of those, so we have to use our best guess, which is to use the sample proportions that we found. Okay? So we can do a little confidence interval for these examples as well. And I'll kind of make the connection to what we were doing before. So I'll come back to this, but I want to show you how we get to that point. So think about when we were doing the difference in sample means. We had population variances, so we could use the z values here. And then we did the square root of each group's population variance over that group's sample size, because each of these represented the variance of each group's sample means. Okay? And the entire thing represented, I'm going to run out of room here. Well, this entire thing here represents the standard deviation for the difference in sample means. That's what we had before. So for our sample proportions, now the statistic we're interested in is just the difference in my sample proportions. Okay? Whenever I have a proportion example, just like with one population, I can use the standard normal or the z-tables. I'll then multiply by, now instead of the standard deviation of the difference in sample means, I need to multiply by the standard deviation of the statistic I'm interested in, which is the standard deviation for the difference in my sample proportions. Okay. What is that going to be equal to? Well, we just said earlier, that's going to be the square root of the variance for the first group's sample proportion plus the variance for the second group sample proportion, similar to what we did up here. It's just how we calculate that variance is going to be a little bit different because we have to use our best estimate, which is the sample proportion from that group times 1 minus that sample proportion over my sample size. I'll then add the same exact thing, but from group 2. Okay? That's where that counts. So, I mean, all this is really following the same procedure here. Just things look a little bit messier, right? Because we have to calculate the variance for a proportion a little bit differently. We're not just given this population variance. Okay? Any questions up to this point? Anything here? And hopefully, I draw this out because I think hopefully this starts to give us a good, we can kind of see that make connections. These are really the similar statistics. It's just proportion versus the mean. All right, so with that in mind, the steps are going to be exactly the same. We've got a couple extra pieces now, and our equation looks a little bit different, but it's really the same procedure, right? So let's say I wanted to do a population proportion or difference in population proportion. So I've got two time periods, 2011, 2010. In 2011, 84% of people were in favor of health insurance for everyone, right? So that was out of 607 people. We had a sample proportion of 0.84. And then in 2010, we had a sample proportion of 0.82 coming from a sample size of 600 people. So if I wanted to build a 99% confidence interval for the difference between 2011 and 2010, what would it be? Well, first of all, I'm just going to write down things so that when we switch over, I have everything ready to go. So the newest time period, we'll call group one. Here I'll write it as 2011, right? So our sample proportion there was 0.84. What was the other one? 2010. Our sample proportion in 2010 was 0.82. Our sample size in 2011 was 607, and our sample size in 2010 was 600. If I want the 99% confidence interval, my alpha should be what? What's the area outside the interval, right? So in decimal form. So my alpha for the 99% level should be 1% outside of it. In decimal form is 0.01. Okay. So when I look at this equation for my confidence interval, I need the z-score that gives me alpha over 2 on each side, right? It's the exact same thing that we're doing when we had sample means. So alpha over the z-score that would give me alpha over 2, or the z-score for what? 0.005 divided by 0.01 by 2 here. So I need to find the z-score that gives me 0.005 in each tail. I'm going to go to my standard normal table here, look up 0.005. It's going to be way up here. So looks like it's in between these two guys. So negative 2.57 and negative 2.58. We don't need the negative sign here. Remember, with confidence intervals, it's already built into our equation, so we just need that 2.58. Okay? Now we should have everything we need to kind of go ahead and calculate this confidence interval. Okay? Now, first thing is, let's see if I can get this all. I'll fold this over because we don't need this anymore. So here is our equation. So we're basing it around the difference in the sample proportions that we found. So 0.84 was our first group. 0.82 is our second group. We've got that z-score of 2.58 we'll plug in. And now here, it's really just a matter of plugging in all of our values, right? And we have the sample proportion, the sample sizes. It's really just a matter of writing it out at this point and getting it entered into our calculator correctly. Now, what might be a good idea is to calculate this intermediate value, which is the standard deviation of the difference in our sample proportion. So find this guy and then plug that in, right? So if I did that, if I can kind of try to have this right here. So if I want to find that standard deviation for the difference in my sample proportions, here it's what, 2011 minus 2010. So we'll take the square root of 0.84 times 1 minus 0.84 divided by 600, and then add in 0.82 times 1 minus 0.82 divided by, wait, this one was, sorry, I flipped these around. This was 607, right? And then this one was 600. Okay? And then once I have that, I can plug in. Well, notice my confidence interval is going to be based around the sample difference I found, which was positive 0.02. So I know that my confidence interval should be based around 0.02. So even if I don't write all this out and calculate it, I can rule out a few answers here. Right? So I look here, which of these, if I'm looking for 0.02, okay, it's in this one, it's in this one. It's not even in this range, so I can rule C out right away, and then it looks like it's in D as well. So I can at least rule one of these answers out because 0.02, the sample difference I found, right, isn't even in the confidence interval C. And it should be not only in it, but smack dab in the middle of it, okay? I'm doing the intermediate calculation just to kind of give you that, what that would be, because I don't think I have it in any stuff. So 0.84 times what? 0.16 divided by 607 plus 0.82 times 0.100, square root of that. So we get approximately 0.022 if I round it. So this was 0.022. You get that entered into your calculator. And then, now this is a little bit easier to enter into my calculator. I don't have like this huge long equation, which is what I would have if I, just kind of did it all at one time. So I really can't stress enough how to avoid a stupid computation error on your calculator to calculate this intermediate step first. It just makes it a lot easier, right? Any questions on this one? So I get this confidence interval with negative 0.03 and positive 0.076. So we'll just use 0.03 and 0.07 to kind of prove my next point. So we've got negative 0.03 is my lower bound, 0.07 is my upper bound. Well, one of the true differences for the, between 2011 and 2012 proportion could be 0. So I can't say, whether or not views have, went up or down, right? I can't say they've increased or the difference is positive. I can't say they've decreased because the value could be negative. In fact, they could, have not changed at all because one of the true values for the difference in this range is 0, right? So, it's I went through all this work, but I really can't say a whole lot, right? Not with this confidence. Now, if I had a confidence interval that was only, I don't know, 0.01 to 0.03, well, now I can say that the people who want to support I forget what the question was, like that healthcare coverage should be available to everybody. Now I can say that more people believe that because now the difference could only be a positive value. So that's how I start kind of using these confidence intervals to do some interpretation here. Okay, so I think we'll end there. I think I have another example that we can kind of work through for confidence intervals. We'll do some hypothesis testing, and then I'll show you how we do that all in Excel as well for proportions on Monday. I believe next Wednesday is that last study day, so we won't have class on Wednesday, and then we'll pick up and start working on sample means, where we only have sample variances next Friday. Okay. All right. I'll see you guys on Monday. Have a good weekend.